In this video, I will show you how to find the particular solution of a differential equation that satisfies an initial condition. Rewriting the equation a tiny bit, I have this. I would like to get all of the y's on the left-hand side and the x's on the right-hand side. So let's subtract x to the 1/2 power from both sides. Now let's multiply both sides by dx to get the dx over here on the right. Now that we have all of the y's on the left and the x's on the right, we can integrate both sides of the equation. To find the antiderivative of y to the 1/2 power, I will add 1 and I will get 3/2. Then I divide by the new exponent. Dividing by 3/2 is the same as multiplying by 2/3. The same thing will happen to x to the 1/2 power. So I will have negative 2/3 x to the 3/2 power plus c. Normally, I would plug in the x and y from my initial conditions right now, but I find that the calculations are a little bit easier if I get rid of this coefficient. So I am going to multiply both sides of the equation by 3/2. That means on the right-hand side, I'm going to distribute. Notice that 3/2 times c is just another constant, which I will call d. Now we use the initial condition to find the value of d. This means that when x is 1, y is 9. So let's substitute 1 for x and y for 9. When you have a fractional power, it means power over root. In other words, this is the square root of 9 raised to the 3rd power. The square root of 9 is 3, and 3 to the 3rd power is 27. So on the left side, I have 27. 1 to the 3/2 power is still 1, so this is just -1. Adding 1 to both sides, we get 28 is equal to d. So let's substitute this back in right here. So right here, this is a particular solution to the differential equation that satisfies the initial condition, but we were also asked to find it in the form y equals f of x. So that means we need to get y by itself. So I am going to raise both sides of the equation to the 2/3 power. Be careful, you cannot do a distributive property with exponents. So I cannot do the 2/3 power separately to each term. I must raise the entire right-hand side of the equation to the 2/3 power. So this is the final answer for number 16. We have natural logs on this one. Neat. Let's start by writing dy dx instead of y prime. We want to get all of the x's on the right-hand side and leave the y, which in this case is just dy, on the left-hand side. So let's start by adding natural log x squared to both sides. Next, I think I will move the dx to the other side by multiplying both sides by dx. Now we can move that 2x over to the right-hand side by dividing both sides by 2x. Now that we have all of the y's on the left and the x's on the right, we can integrate both sides of the equation. Integrating dy is like integrating a 1. So the antiderivative will just be y. To integrate the right-hand side, let's use u substitution. Let's let u equal the numerator, natural log of x squared. Now, what will u prime be? The derivative of natural log something is 1 over something. So this will be 1 over x squared. Because this is not just an x, we need to do the chain rule and multiply by the derivative of the inner function, which is 2x. Notice that the x in the numerator cancels out one of the x's from the denominator. So u prime simplifies to 2 over x. Let's do the substitution. So we have y equals the integral of natural log x squared is u. So we have u over 2x. Instead of dx, we will write du over u prime. But u prime is 2 over x. These x's will cancel each other out, and we will be left with 2 times 2 is 4. This 4 in the denominator can be brought out as a 1/4 in the front of the integral. So we now have 1/4 of u du. The antiderivative of u is 1/2 u squared. We still have the 1/4 here in the front. So this is really going to be 1/8. Substituting natural log of x squared back in for u, and we have this. This is a general solution to the differential equation, but now we need to find the particular solution by using the initial condition to find the value of c. This initial condition says that when x is 1, y is 2. So let's substitute 1 for x and 2 for y and solve for c. So on the inside here, 1 squared is 1. We have the natural log of 1. We know that is 0. 0 squared is just 0. 1/8 times 0 is 0. So this entire term has a value of 0. That means that c is equal to 2. Substituting 2 in for c, and we have a particular solution to the differential equation that satisfies the initial condition. There is another version of the answer that you might see as an option on a multiple choice question. Quick side lesson: if I have the natural log of a to the c power, a property of logarithms is that this exponent is allowed to come to the front. So I could write this as c times the natural log of a. So on the inside here, we have the natural log of x squared. I could rewrite this as 2 times the natural log of x. So if I do that, then that expression is being squared. And we have the 1/8 out in the front. Y equals all of it. I can square the 2 and the natural log x. 2 squared is 4. So I'm going to have y is equal to 1/8 times 4. And then there's not a lot I can do with the natural log of x squared. It's still going to look like this, natural log of x squared. But the 1/8 times 4 simplifies to 1/2. So if it's a multiple choice question, the answer may be written this way instead of this way. Anytime natural log is involved, because of the properties of logarithms, there are always multiple ways of writing the answer. So just be on the lookout for that. Number 20. Ultimately, I need all of the y's on the left and the x's on the right. But first, I'd like to fix the fact that this is a subtraction problem by adding this term to both sides of the equation. At the same time, I went ahead and wrote y prime as dy dx. Let's move that dx over to the right-hand side by multiplying both sides by dx. So now I have this. I want all of my y's on the left and x's on the right. So I really want this radical 1 minus x squared to be over here. And I really want the 1 minus y squared square root to go over here. So let's divide both sides of the equation by each of these radicals. So the radical 1 minus x squared is going to end up in the denominator over here, and the radical 1 minus y squared will end up in the denominator over here. Now that we have all of the y's on the left and the x's on the right, we can integrate both sides of the equation. If these x's and y's were 1's Instead, we would integrate using arc sine. But since it's y and y squared, it's going to be u substitution. So let's let u equal 1 minus y squared. And that means that u prime will equal negative 2y. At the same time, we have to do u substitution with the x's, but we already used the letter u. So we have to call it something else. So how about v? Let's let v equal 1 minus x squared. And v prime will equal negative 2x. Performing this substitution, we have the integral of y over the square root of u. Instead of dy, we will write du over u prime, which is negative 2y. And then on the other side, we have the integral of x over the square root of v. And then instead of dx, we will write dv over v prime, which is negative 2x. On the left side, the y's cancel out. This negative 2 in the denominator will come out in the front as negative 1/2. So we have negative 1/2 times the integral of 1 over the square root of u du. Something similar happens on the left-hand side. The x's cancel out. We have the negative 1/2 in the front times the integral of 1 over the square root of v dv. Let's rewrite these fractions with negative exponents, but at the same time, since we have negative 1/2 on both sides of the equation, we can divide both sides by negative 1/2, and that's gone. For the antiderivative of u to the negative 1/2 power, we add 1 to the exponent and we get u to the positive 1/2 power. Dividing by the new power, dividing by 1/2 this is the same as multiplying by 2. And then similarly, we will have 2v to the 1/2 power plus c. Let's substitute 1 minus y squared back in for u and 1 minus x squared back in for v. This is a general solution to the differential equation. For a particular solution, we need to find the value of c using the initial condition. This means that when x is 0, y is 1. So let's plug in 0 for x and y for 1. 1 squared is 1, so we have 1 minus 1, which is 0. 2 times 0 is 0. So on the left-hand side, we just have 0. Over here, this is just the square root of 1, which is 1. So we just have 2 plus c. Subtracting 2 from both sides, we get c is equal to negative 2. Let's substitute this in right here. This is a solution to the differential equation that satisfies the initial condition. Sometimes we can stop here, but we were asked to write the solution in the form y equals f of x, so let's keep going and get y by itself. I'm noticing that every term has a 2 in it. So let's divide both sides of the equation by 2 and get rid of all of these 2's. Next, if I square both sides, the radical will go away. So now we have this. On the next step, I will subtract 1 from both sides. On the next step, I will divide both sides by negative 1. That'll make this negative sign go away and show up here, and this will be positive. Finally, I will get y by itself by taking the square root of both sides. Don't forget the plus or minus. We are almost done, but not quite. The reason is because of the plus or minus. Only one of these is the correct answer. It is either plus or minus, but not both. So how do we decide which it should be? We need to look at the initial condition. When x is 0, y should equal 1, a positive 1. Now, look back at the expression. This part of the expression with the square root can only be positive. You cannot take the square root of something and get a negative number. So, if I take something that is positive and then put a negative in the front of it, obviously it's going to be negative. And that is not what we want. We want to be able to put in 0 for x and get a positive 1 for y. The only way that will happen is if there's no negative in front and if it is just left to be positive. So this is the final answer. But notice that if the initial condition had been y at 0 is equal to negative 1, then the answer would be y equals negative square root. To solve number 22, I will use properties of exponents. So quick side lesson. Let's say I had e to the a power times e to the b power. When you multiply with like bases, you add the exponents. So that would give me e to the a plus b. But guess what? This process is reversible. So if I had e to the a plus b power, I could rewrite this as a product by writing e to the a times e to the b. Well, this property is what I'm going to use right now. E to the r minus 2s power can be written as a product e to the r power times e to the negative 2s power. I want to get all my r's on the left and all of my s's on the right. Let's multiply both sides by ds to get that ds over on the right. Now let's get e to the r to the other side by dividing both sides by e to the r. But instead of leaving it as 1 over e to the r, let's write it as e to the negative r. Now that we have the r's on the left and the s's on the right, we can integrate both sides of the equation. Let's find the antiderivative using mental u substitution. Imagine that u is negative r. That means u prime is going to be negative 1. So to compensate, all I need to do is put a negative out in the front, and now I can just go ahead and take the antiderivative. The antiderivative of e to the u is just e to the u plus c. Same deal over here, except this time imagine that u is negative 2s. So u prime is negative 2. That means we will end up dividing by u prime. We will end up dividing by negative 2. So out in the front, I will need a negative 1/2. Other than that, I can proceed with the antiderivative. The antiderivative of e to the u is e to the u plus c. It's time to find the value of c by plugging in 0 for s and for r. E to the 0 power is 1, so on the left side I have negative 1. And again, e to the 0 power is 1, so I just have negative 1/2 plus c. Adding 1/2 to both sides of the equation, and I get c is equal to negative 1/2. Let's plug that in right here. This is a particular solution that satisfies the initial condition. Sometimes we can stop here. But let's keep going and see if we can get r by itself. For starters, let's divide everything by negative 1. To get rid of this e, I'm going to take the natural log of both sides of the equation. Base e and natural log are inverse functions, so they will cancel each other out. On the next step, we will just have negative r. And for the last step, let's divide both sides by negative 1. So this is the form of the solution that has r by itself. I want to just briefly show you another version of the answer, just in case you run into a multiple choice question. First of all, notice that both of these have a denominator of 2. So I could combine these into one fraction by having e to the negative 2s plus 1 all over 2. Now, properties of logarithms. Remember that if I have c times the natural log of a, I can take that c and put it as an exponent. So I could write this as the natural log of a to the c power. I could take this negative 1 in the front and put it as an exponent inside the logarithm. So I think I'll just do that kind of real quick. So I could take that negative and put it up there instead. That would have the effect of turning the fraction upside down. So you might see the answer written this way. So if it's a multiple choice question and you don't see this, look for this.